let's look at another selective precipitation problem. If we've got potassium hydroxide in the previous example, when the hydroxide ion minus concentration reaches 1.9 times 10 to the minus 6, the magnesium hydroxide begins to precipitate out of solution. As we add potassium hydroxide, the magnesium hydroxide continues to precipitate. At some point, the hydroxide ion concentration becomes high enough to begin to precipitate the calcium ions as well. What is the concentration of magnesium 2 plus when the calcium begins to precipitate? All right, so this is set up as kind of a tricky problem. It's not something that you can just kind of look at and go, oh yeah, it's going to be this, right? Because these two things are tied into each other. It's got this common ion here, but we can still use our concepts from equilibrium to figure out when the calcium begins to precipitate and when we've got that calcium precipitating, what's the hydroxide ion concentration? Use that for the KSP and magnesium. So the first thing we need to do is figure out the hydroxide ion concentration when the calcium starts to precipitate by writing a Q expression for the calcium hydroxide and substituting in the concentration of calcium and that we had before. So Q was equal to calcium times hydroxide squared. So that's the products. Right? And it should be over 1 because it's the solid. So we got 0.011 from before times the hydroxide ion concentration squared. We set the expression for Q to be equal to K. So that's that threshold value. Right? So when Q is equal to K, then we'll start to see the precipitate happening. If it goes over that, Q becomes bigger than K, precipitate forms. So Q is equal to K, and K was 4.68 times 10 to the minus 6. So we're going to rearrange and solve for the hydroxide ion concentration. Divide by 0.011, unsquare it, and we get 2.06 times 10 to the minus 2 molar. So that's when the hydroxide ion concentration reaches 2 times 10 to the minus 2 molar, we're going to start to precipitate out the calcium. Now we need to figure out the concentration of the magnesium at that hydroxide ion concentration. We reestablish our Q, but this time for magnesium hydroxide, so MgOH2OH squared. So magnesium, we're going to solve for this. We just calculated that hydroxide ion concentration. We put that into there. So when Q is equal to K, the magnesium ion concentration is 2.06 times 10 to the minus 2 squared, which is equal to the K for the magnesium. Right, so this is going to act to suppress the magnesium concentration. Rearrange, solve for magnesium 2 plus 4.9 times 10 to the minus 10 molar. So our selective precipitation worked well. The concentration of magnesium dropped from 0.059 molar to 4 times 10 to the minus 4 molar before any of the calcium began to precipitate, which means that 99.99% of the magnesium was separated from the solution. Yep. And we can use this idea of selective precipitation and qualitative analysis of metals in solution, which you guys will probably do in a lab. So it's sometimes called qual analysis, qualitative analysis. So you've got two different ways you can address knowledge. It can be either qualitative, what is it, or quantitative, how much do I have? And this qualitative analysis scheme is used to identify different ions in solution, and it's used for the analysis of 20 common cations that are organized into 5 different groups. And we've got a little flow chart or schematic that goes with how this qualitative scheme works. So you start off with a solution containing all the ions from all the cation groups. You add in some HCl and filter it. And so you're going to add in some HCl. If there is silver, mercury, or lead, those chlorides are insoluble. So the group 1 will precipitate out if we add HCl. We then have the supernatant, or unprecipitated stuff, containing groups of, so this will have groups 2, 3, 4, and 5. You add H2S to that. Right, the H plus isn't going to react with anything because we already got HCl in there, so it's the sulfide, so we'll precipitate out the sulfides of copper, cadmium, mercury, tin, and bismuth, although all of the mercury should have been precipitated out before. So that will leave so the group 2 is out, so now we just got groups 3, 4, and 5. So the solution has all the remaining stuff in it. So you add some sodium hydroxide, you neutralize your HCl. Right, the sodium is not going to do anything. You're going to shift the pH the other way, and you're going to add until you precipitate out cobalt sulfide, iron sulfide, magnesium sulfide, nickel sulfide, zinc sulfide, and then aluminum hydroxide and chromium hydroxide. So these are going to be pH dependent, right? And or they're going to have hydroxide as an insoluble component. This means that all that's left is group 4 and 5. You add some carbonate, sodium carbonate, and barium carbonate, calcium carbonate, and strontium sulfate will be left. They'll precipitate out. Anything left over is going to be a solution containing just our sodium, potassium, and ammonium ions. You can then do a flame test. Right? Flame test, for example, is going to tell you whether you've got yellow, if it's sodium, or potassium with the blue flame. Right? Our last aqueous equilibria thing that we can address is complex ion formation. So this is looking at things like a Lewis acid. So transition metals tend to be good Lewis acids. They often bond to one or more water molecules to form a hydrated ion, in which case water is the Lewis base and it donates an electron pair to form a coordinate covalent bond. So Ag plus in solution is actually not going to just be Ag floating around. It's going to form this hydroxide complex where there's some water that's associated with it. And ions that form by combining a cation with several anions are called complex ions. So for example, AgH2O2 plus is a complex ion. Ions attached to ions or molecules are called ligands. So in this case, the ligand from the Latin ligare, to tie, like ligature. So this ligand is tied to the silver, and it's water in this case. A ligand is added to a solution that forms a stronger bond than a current ligand. It will displace or replace the existing ligand. So Ag with 2 water ligands, if I start mixing in some ammonia, the bond between the silver and the ammonia is stronger than the bond between the silver and the water. So the ammonia comes in, kicks out the water, and now I've got this complex with the AgNH3, the silver ammonia complex, and water. Generally, because we're working in an aqueous solution, water is not included because its complex ion is always present in an aqueous solution. So we'll just kind of leave the water part out and we'll say Ag plus 2NH3 gives us AgNH3 2 plus aqueous. And so this guy's going to all float around as one thing and with a plus charge. Right, so it's this plus charge from the Ag, and then the NH3 is neutral. The reaction between an ion and ligands to form a complex ion is called complex ion formation reaction. So this is a complex ion formation reaction, and we'll give it the equilibrium expression Kf. So Kf is going to be products over reactants. And in this case, it's very similar to KSP, but note that you've got the one thing over here that's coming from two things. So I've got the Ag plus and the NH3 that are the reactants, and then the complex, the AgNH3, that is the products. Right? And because this is a formation of a complex ion, we'll call it K sub F for formation. And different chemical species have different Kf values. Right, so AgCN 2 minus has a Kf of 1 times 10 to the minus 21, and AgNH3 2 plus has a Kf of 1.7 times 10 to the minus 7, and of course you can imagine all those sorts of things that we just saw with selective precipitation can happen, right? So if I've got Ag with water, the Cn minus will come and displace that. And then if I put in some NH3, the NH3 will displace the Cn into solution. Right? And so I'll form this preferentially over this. Something like aluminum, right? I've got different things for different aluminum compounds. So it's hard to predict. Notice that unlike KSPs, these guys tend to be large positive numbers, right? The KSPs tended to be very small numbers, 1 times 10 to the minus 5, 2 times 10 to the minus 20, right? These are 1 times 10 to the 21, 2 times 10 to the 43, right? Very, very big numbers over here. This is just another table, but I like this because it actually writes out the equilibrium equation for you. Right? So it's showing you what the reaction is, not just what the complex is. So let's do an example. I mixed 200 milliliters of a solution that's 1.5 molar times 10 to the minus 3 molar copper nitrate with 250 milliliters of a solution that's 2 molar NH3 after the solution reaches equilibrium. What's the concentration of any copper 2 plus that is free? Right, so same setup as like we did with any of our equilibrium problems. We're going to start off with a balanced chemical equation. Here it's copper 2 plus 4 NH3 goes to the copper ammonia complex. And it's got a Kf of 1.7 times 10 to the minus 3. This is a large number. This product is favored. Right. First thing we need to do is figure out the concentration, our initial concentration of the copper. So we'll take our 2 liters, or 0.2 liters, and the concentration to give us moles, and then we're going to divide by the total volume because we mixed 200 milliliters and 250 milliliters, and I get 6.7 times 10 to the minus 4 molar copper. Do the same sort of so once you figured out the ammonia concentration, we're ready to set up our equilibrium table. So our initial concentration of copper was 6.7 times 10 to the minus 4. Our concentration of ammonia was 0.11 moles per liter. Our concentration of the complex was 0. We're going to change or lose some of this. Since the equilibrium constant is really big and the concentration of the ammonia is way, way, way larger than the concentration of copper, we're going to assume that all of the copper gets used. In this assumption, we're going to let X represent the concentration going to equilibrium. Here we're going to let X be the small amount of copper that remains when the equilibrium is reached. So this is a little bit different setup. This is leftover copper. We're going to assume most of this is going to be used. Right? So X is going to be our unknown amount. And that's the leftover bit. So we're going to substitute the expressions for the equilibrium concentrations into Kf and solve. So products over reactants, 6.7 times 10 to the minus 4 divided by X times 0.11 to the 4th power. Right, rearrange to solve for X, 6.7 times 10 to the minus 4 divided by Kf times 0.11 to the 4th. We end up with 2.7 times 10 to the minus 13, since X is 2.7 times 10 to the minus 13, which is way, way, way smaller than 6.7 times 10 to the minus 4th. The approximation is valid. The remaining copper concentration is 2.7 times 10 to the minus 13. So let's look at how we can affect the solubility with complex formation. Right? So if we've got a solubility of an ionic compound containing a metal cation that forms a complex increases in the presence of aqueous ligands. Why is that happening? Right? So I've got AgCl solid and Ag plus and Cl minus. Well, if I can pull away some of this Ag plus by forming a complex, what does Le Chatelier's principle say? It should move it to the right. I should make less of this and more of this. So if I can somehow get rid of this, right, by pulling it away and forming a complex, I should shift it to the right. So my KSP for this reaction is 1.77 times 10 to the minus 10. The KF, so the KF for this is 1.7 times 10 to the 7, so it's a very, very large number. So what happens is I've got the Ag plus in equilibrium. Every once in a while, a little Ag pops up. But if I put the ammonia in that solution, anytime the Ag pops up in there, and when it does, it puts in a Cl minus as well, that Ag from the Ag solid is going to form the Ag NH3 complex. And so I will consume the Ag plus in solution, or consume the Ag plus in solution, and form the complex. And when I do that, now it's no longer at equilibrium. I need to put stuff back into solution. Right? So if I look at adding in NH3 here, the solubility of the silver chloride is going to go up and up and up and up as I increase the concentration of NH3 that I added.